It takes Jupiter 12 Earth years to orbit our sun. Can you imagine a planet the size of Jupiter, 10 times the diameter of Earth, whipping around its own star in 2.5 days? What about a planet that may be covered in diamonds? Or planets tidally locked to their sun like the moon is to Earth, one side eternally roasting and the other side locked in frigid darkness? Can you conceive of an ocean world where the entire surface is covered by water with no land at all? Or a planet where it rains glass? Or how about a planet that orbits a pulsar? Well, these are not the imaginings of Arthur C. Clarke or the writers of Star Trek. These are real worlds that we have begun to explore, albeit from a great distance. These are exoplanets. One of the great things about cosmology, astronomy, and astrophysics is that these are the gifts that keep on giving. The more we learn about the universe around us, the more fantastic, wondrous, and even mysterious it becomes. Each new discovery gives rise to 10 new questions and dozens of new theories. In tonight's SETI Talk event, we revisit one of our favorite topics, exoplanets, a relatively new field of astronomy and astrophysics dating back to the mid-1990s, when the first verified discovery of an agreed planet orbiting another star besides our sun was discovered. Not actually the first such discovery as it happens, but the first agreed discovery. Since that time, our understanding has truly exploded, with thousands of confirmed new exoplanet discoveries occurring with dizzying frequency, most notably from NASA's Kepler mission and its successor TESS mission. The discovery of exoplanets is one of the most profound revelations since Nicholas Copernicus put the Earth in its rightful place, orbiting the sun instead of the other way around. Our new understanding that exoplanets are not only common, but indeed ubiquitous in our galaxy and likely the same in others, has forever changed our perspective as to our place in the universe. But we've learned something else. Some of these exoplanets are really weird. And tonight, we're going to learn more about them. So good evening, good morning, and good day, ladies and gentlemen, and welcome to our February 2021 SETI Talks lecture. SETI Talks is the monthly lecture series produced by the SETI Institute in Mountain View, California. I'm Bill Diamond, President and CEO of the Institute. We are a nonprofit research and education institution whose mission is to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe and to share our work with the world. Our SETI Talk series has been running for more than 10 years, and if you visit the archive on the Institute's YouTube channel, you'll discover hundreds of lectures, debates, and panel discussions featuring many of the world's foremost researchers, educators, and explorers in space science, covering an extraordinary range of topics. Almost 1 year ago, the coronavirus compelled us to convert the talks to a virtual online series, but that means we now reach a global audience, and we're delighted to have all of you with us this evening. I'd like to welcome our registered guests on Zoom and also say hello to everyone joining from our other platforms. As our regular attendees know, we love to find out where you're joining us from. So if you're on Zoom, use the chat function at the bottom of your screen to give us your coordinates. And on Facebook, use the comments section and let us find out how far we're reaching across our own planet tonight. We also like to poll the audience to find out who's joining us for the first time and who's a habitual fan. If you're with us on Zoom, you'll see a pop-up on your screen where you can select the answer that is the most appropriate and hit the submit button. We'll then share the results in just a bit. To further explore the weird and wonderful world of exoplanets, we have invited two extraordinary young astronomers who've devoted their careers to the study of exoplanets and are particularly fascinated by the strange ones. We're joined by an assistant professor of astronomy studying exoplanets with particular focus on habitable worlds, and also by an award-winning astrophysicist currently supporting NASA's TESS mission to find the nearest planetary systems. The moderator for tonight's discussion is our own Dr. Frank Marchese, senior astronomer at the SETI Institute and senior scientist for Unistellar, who bring deep space observations to amateur astronomy through their amazing EV scope. We will have time for audience questions after the moderated discussion. We'd prefer if you would hold off until our guest speakers have made their initial remarks before you start putting questions up for addressing them. If you're watching on Zoom, you can post your questions using the Q&A feature that you see also at the bottom of your screen. My colleagues Rebecca and Beth will be fielding your questions. We'll do our best to answer as many as we can, but please understand we probably won't be able to get to them all. Finally, before we get started, I want to make you aware of some terrific upcoming events you might be interested in. Tomorrow, February 18, join us for a very special SETI Live event covering NASA's Mars 2020 mission and the landing of Perseverance rover. Our coverage begins at 11:15 Pacific time, culminating with the hopefully safe touchdown around 12:30 Pacific time. Frank and Beth will be the anchors of this event with a long list of special guests, so you can join us live at 11:15 Pacific time tomorrow on Facebook or YouTube. And on the 23rd of February, we continue our Space Science for Families series. This is a lecture series in partnership with the Chabot Space Science Center in Oakland, California. Dana Bachman will talk about NASA's SOFIA Flying Infrared Observatory from 7 to 8 p.m. Pacific time. And you can again join us on Facebook and YouTube. And be sure to come back for our March SETI talks that will be on Wednesday, the 24th, where of course, the topic will be the Perseverance rover. It'll be featuring one of our instrumentation and payload scientists, Pablo Sabran, and other guests. Once again, that'll be at 7 p.m. Pacific time on the 24th, and registration will open on March 10. Lastly, as you will learn about some weird and wonderful worlds beyond our solar system tonight, at the end of the talk, you'll have an opportunity to vote for your favorite. So you want to be sure to hang on for the vote and the results. So with that, let's buckle up and go exploring and venture to new worlds far beyond Earth. I will now turn the proceedings over to Frank Marchese, who will introduce our speakers and get us started. Frank?
Thank you, Bill. Thank you very much, everybody. I see we have more than 400 people here watching us from everywhere in the world, even from different countries and places. So welcome. So today we are going to talk about weird exoplanets, the weirdos of our galaxies. And we're gonna find out probably that there is a lot of weird exoplanets. And for this, because there is so many of them, we invited two scientists, two renowned astronomers who have been dedicated a career working in the field of exoplanetary science. So first of all, Andrew, how are you? Andrew is hi, sorry, you can unmute now. Andrew is an assistant professor at the University of Wisconsin-Madison. His research focuses mostly on the studying of exoplanets. He would like to answer to one of the most interesting questions we have at the moment: are the planets orbiting around other stars throughout the galaxy potentially habitable or similar to our solar system? Andrew has received a bachelor degree at UC Berkeley in 2013 and a PhD from Harvard in 2017. And close to Andrew, we have Jessie Christiansen. Hi, Jessie.
Hi, everyone.
Jessie is an astrophysicist with the NASA Exoplanet Science Institute at Caltech. She searches and characterizes, catalogs planets orbiting around other stars, exoplanet. And in 2018, she was awarded the NASA Exceptional Engineering Achievement Medal for a role with the successful NASA Kepler mission, which has discovered thousands of exoplanets. And you are going to talk about that probably today. She now works on the NASA TESS mission, the Transiting Exoplanet Survey Satellite, which is dedicated to find exoplanets, but this time nearby us. And probably you are going also to talk about this. So Jessie, you ready? Let's buckle up and start talking about exoplanets.
Thank you so much, Frank. I'm going to get this started. Hi, everybody. Welcome. I'm so excited to talk about weird and wonderful exoplanets tonight. It's very hard to pick my favorite weird exoplanets because the truth is every planet we find is weird and interesting and different. That's the best part about it. But just to take a quick step back, what are exoplanets? Here's a schematic of our solar system. And I know everybody right now is focused on this red planet right here, just the next one out from Earth, because that's very exciting. Perseverance landing tomorrow. So our sun is a star, boring middle-aged G star, and it has 8 planets. We can have a whole separate talk about Pluto. But for thousands of years, we've looked at the other stars in the sky and wondered if they have planets around them too. And it's only in the last 25 years that we've been able to discover that, yes, they do. And as Bill mentioned, it seems like planets are ubiquitous, but not necessarily the sorts of planets we have in our solar system. So here's a quick walkthrough of our solar system. We have planets, we have dwarf planets, we have minor planets. We don't have exoplanets because exoplanets are around other stars. Here's a kind of very quick overview of what we've found so far. This axis here is showing how far away from the star the planet is, starting with very, very close stars of planets to very, very far away planets. And this axis here is showing how big the planet is. So little planets are down here at the bottom and big planets are up here at the top. This little pink square here is Earth. That's where Earth would be on this plot. So you can see that all of the things we've discovered so far, there's 4,000 planets on this plot, don't look like the Earth. They look very different. One of the types of planets we've discovered are Jupiter-sized things way up here, 10 times the size of the Earth, that orbit their star in just a few days. So I want to very quickly talk about one, HD 1897333b, and I apologize for the names. They're all garbage names. Please forgive us. This is the one that Bill mentioned. So this is a planet that the wind is so hot because the planet is so close to its star and moving so quickly because it's so superheated. And we've been able to tell that it's silicate rich. So silicates is sand and glass. So what happens if you heat sand up to thousands of degrees? It becomes liquid glass. So this is a planet where it's raining liquid glass sideways constantly. It's just a pure hellscape. Very weird. Another kind of planet that we found is much smaller, but even hotter, and we call them lava worlds because they are like blobs of lava floating in space. So one of them, 55 Cancri E, which I'm showing here, is a little ball of rock that's so close to its star that the surface of the planet that's facing the star has been completely melted. It's just lava on that side and then rock on the other side. And this one we found is likely to be carbon rich. And what happens to carbon when you heat it up and squeeze it? It becomes a diamond. So one possibility is this planet has a diamond layer inside. You know, Tiffany's Eat Your Heart Out. We've got a whole diamond planet here. We have a bunch of mysterious planets that we call them super Earths. Now, we don't know what super Earths are yet because we don't have one in our solar system. It's between the size of Earth and Neptune. But we did find some smaller stars, some more big planets like Uranus and Neptune, and we did find some small planets. One small planet I wanted to talk about is not weird because of the planet. It's weird because of the star. So this is Kepler 186f. It's a rocky planet that's the right distance from its star to have liquid water on the surface, which is like the holy grail of what we're looking for with exoplanets. We want to find something like Earth. Unfortunately, the star that it's orbiting, this red star over here, is very different from our sun and puts out a lot more high energy radiation, so UVs and X-rays. Now, this is bad for life. You know, this is why the dentist makes you wear the lead apron, because X-rays are bad. So we have this rocky world that's the right temperature, but it might be completely blasted by high energy radiation. So we have no idea if these rocks around M dwarfs are habitable or not, but it's super interesting to think about. The very last weird system I wanted to show is a system of super Earths. It's a system of these mystery planets. And what's weird about this system is the configuration. This system is called K2138, and it's got 5 planets in a chain of resonances. So the period of each planet is related to the period of the next planet. And the cool thing about resonances, they make music. So because these planets are in this chain of resonances, if you turn the orbits into notes, it plays a song. And it actually sounds nice because the planets are all in resonance with each other. So this is K2138, which is this very weird musical system. And it was founded by citizen scientists. And I know that people who listen to SETI talks are super exciting citizen scientists. So please come and help us find new planets with TESS at this website. So those are my 4 weird planets. And now we'll move on to Andrew's favorite weird planets. And I will stop sharing.
Thank you, Jessie. So Andrew has 5. We give him one more to tell us about. Go ahead, Andrew.
Thanks everyone for coming. I'm really excited to be here to show you some of my favorite weird exoplanets. So the first planet that I'm going to talk about is a baby planet. This is called AU Microscopy b, although astronomers usually shorten that to AU Mic b. This planet is only 22 million years old. Now, that probably sounds pretty old to most of you, but if we consider how long stars live, our sun is 4.5 billion years old. It'll last for almost 7 billion more years after this. If our sun were a person, it would be middle-aged, about 35 years old. AU Mic b, on the other hand, the planet and that star are so young that if they were a person on that same scale, they would only be 2 months old. This planet may be able to help us learn how planets change as they grow older. You and I both changed a lot since we were 2 months old. Perhaps planets do as well. Here's a picture of AU Mic b. This is a real image. This is from the Hubble Space Telescope, and this is from the SPHERE instrument on the Very Large Telescope in Chile. This weird billowing cloud is what we call a disk. This is the material from which planets are born. And now we know very close to the star, way inside of anything we can see in this image, that there is a planet around this star, AU-McB. Here's an image of that right here. It's about the size of Neptune. And we're very interested in learning more about it and seeing how different it is from the planets in our own solar system that have been that have grown older. Another very unusual exoplanet that was discovered just in the last year is called Ogle 2016 Bulge 1928. Another mouthful, I know. This planet, though, doesn't have a star anymore. We think that long ago it was part of a system, it formed around a star, and then got into a gravitational wrestling match with another planet, lost, and was shot out of the system like that planet right there. We discovered this planet with only 4 hours of observations. This graph is the real data that was used to find this planet. The y-axis shows how bright the star appeared as a function of time, and over on the x-axis it shows how long they were observing. So over the course of about 4 hours, a star got a little bit brighter because light from that star was bent towards us by this planet, floating free in space, thanks to Einstein's theory of general relativity. We will never get to see this planet again. We'll never see any light from it, but we know it's there because of this little blip. We think that this planet is probably about the mass or the weight of Earth and Mars, but really the characteristics are unknown because we have so little information on it. But it hints at this large group of planets that may be roaming the galaxy free without a star of their own. The next planet that I want to talk to you about is called KOI 1843.03. This planet is one of those hot Earths that Jessie just talked about. This planet orbits extremely close to its host star. This diagram is to scale. Here's the star and here's the planet. It's barely skimming the star's surface. It's so close to its star that it only takes about 4 hours for it to go all the way around in its orbit. If you lived on that planet, which I don't recommend, by the way, because it's very hot, you would have birthdays every 4 hours. The other amazing thing about this planet is that it's so close to its star, it's being stretched by the star's gravity, so that instead of being round like the planets in our own solar system, it's been stretched into the shape of an American football. And this is about how we think it looks, based on how we know that rock will stretch when it's got such a strong gravitational force applied to it. The last 2 planets that I want to talk about answer a slightly different question. In particular, what happens to planets when their host stars die and run out of nuclear fuel? In about 7 billion years, our own sun will run out of hydrogen in its core that it uses to burn into helium and warm our planet. When that happens, it will swell up to a huge size. It will engulf most of the inner solar system. Unfortunately, probably won't be a great time to be on planet Earth here, but hopefully we may have been able to move on by then. Then it will shed the outer layers of the star and leave behind a small, smoldering core called a white dwarf. Sometimes, though, the planets that survive this, the ones that orbited far away originally from the star, can make the journey back in. It's a perilous journey, though. One planet that we know of orbiting a white dwarf is called WD 1145 plus 017b. And this planet is not really an exoplanet, it's an exoplanet. We think it's being ripped apart by the star's gravity, a more extreme example of what was happening to KOI 1843.03. But this time it's being stretched so hard that it loses little chunks every so often, just like this. And these chunks orbit around, eventually collide with other things, show a poof of dust, which we can see with our telescopes, and then vanish. We don't know how long this planet is going to be looking like this. It's been around for at least 5 years. We don't know if it'll be around tomorrow. We hope it does, though, because we'd love to learn more about it. And finally, there are some planets that actually can survive the journey. Instead of being pulled apart like WD 1145 plus 017b, some planets, like the newly discovered WD 1856 plus 534b, actually can survive. This planet is about the size of Jupiter, and it's orbiting a white dwarf star. White dwarfs are very small. Jupiter-sized planets are large, so this star is actually smaller than its planet. This star is an ancient star. We think it's about 10 billion years old, and it has been about 5 billion years since it originally ran out of fuel. So this planet could be orbiting around the star for much longer to come. So with that, I am done with my planets, and I think now we have a discussion.
Thank you very much to both of you. It's amazing when I see your presentation. I mean, I knew the planets you will present in advance, but frankly, it's absolutely amazing to see this diversity into this world of exoplanets and those extreme worlds. I have a very basic question that I did not prepare you for, but I want to ask you that because I know people are wondering why those planets have these weird names, which look like phone books, numbers, etc. Could you give us a short overview of why we're using those names?
Sure. So since I'm the planet archiver, I'll have a stab at that one. So there's a fairly strong tradition established in astronomy by binary stars. So we knew about binary stars long before we knew about exoplanets. So binary stars is when two stars are going around each other. And we call them capital A and capital B. Now, the name that goes, the phone number that goes in front of the capital A and capital B basically comes from big surveys. Someone goes out and looks at the sky and says, all right, that's 1, that's 2, that's 3. And there's a lot of stars in the sky. So eventually you get up to, that's 189,733. So all of the stars in the sky have numbers, and there's a whole bunch of different catalogs. So part of my job is making sure we get the right name from each catalog. So you take that name of the star, and then when you find a planet around it, you add a B, but you don't add a big B, which would mean it had a star around it. You add a little b to show that it's a planet, not a star. And then if you find more planets, you add a little c and then a little d and then a little e. So 55 Cancri E, for instance, was the 4th planet we found around the star 55 Cancri. So they're really, really, really garbage names, mostly because there's so many stars in the sky, it's frankly impossible to really give them all quite meaningful names. Although the IAU did try a few years ago to give some of the planets more interesting names.
That's correct. Thank you. Thank you for having this out of the way. We are going now to talk about the science more than the name. So something that come out when I hear you talks, of course, is there is a lot of exoplanets. And you mentioned that we have seen a wide diversity of them, but we have not seen something like our solar system, apparently. Something like with 2 giant planets and a lot of terrestrial planets, small, the size of Earth and smaller. So does that mean that we are the weirdo of the galaxy?
Not so far. So basically, finding Earth, finding a true rocky planet at the right distance from a star like the sun to have liquid water is still just beyond our detection sensitivity. So we've built bigger and better instruments all the time, and we're getting closer and closer to finding something like Earth. But right now, we're still just not really sensitive to a true Earth in a true Earth-like orbit around a star like the sun. So that plot that I showed that had all of those bigger, hotter planets, it's because they're easier to find. They make a bigger signal that we can see. But one of the things we can do, and we do, which is very dangerous, but we do it anyway, is extrapolate. So we take the smaller things and we take the hotter things and we say, okay, if this trend continued, could we guess how many Earth-like planets there are? So we've done that in many different ways with the Kepler data. And our guess is that there's something like between 10 and 50% of stars like the sun have a planet like Earth. So that's actually pretty high. That's up to half of the stars like the sun. And the galaxy has billions of stars like the sun, have a planet like the Earth. So it might be that we're not weird. We just haven't found anything like us yet because the detector technology is not quite there.
So that's a detection bias, basically.
Exactly. It's a detection bias. It's harder to find Earths, so we haven't found any yet. But we think that they're out there.
So Andrew, you think that one day we are going to find Earth-like exoplanet, but they may be very weird, right?
Absolutely. Yeah, I think our technology is rapidly progressing. We right now only have the technology to see maybe 2, maybe 3 at most of the planets in our solar system. So in the next couple of decades, we hope that we're going to be able to find these Earths. But will they be anything like the planets in our own solar system? That's a great question. We just don't know the answer to that. We need to be able to learn more about these planets than we can today. Hopefully, we'll be able to even learn what these planets are made of. Do they have rocky compositions similar to our own planet, where we have a small iron core and a silicate-rich mantle? and then a little thin crust on top? Do they have atmospheres like our own Earth, where we have a very thin atmosphere made mostly of heavier gases like oxygen and nitrogen? Or are there some planets that could potentially be habitable that have an atmosphere made of hydrogen or helium on their surfaces? There's lots of questions, and at this point, we're still just barely scratching the surface of that exploration.
Yeah, and we're scratching the surface of that exploration, but we have seen something already weird in all those surveys, the TESS and the Kepler. We've seen those super Earth. You mentioned them briefly, Jessie. So maybe you can kind of describe truly what we think they are and the science behind it.
Yeah, so I mean, before we found any exoplanets, the only real model we had was our solar system. And our solar system really kind of diverges into two size ranges. There's like the small rocky planets, Mercury, Venus, Earth, and Mars. And then there's the big ice and gas giants. And there's actually a pretty big jump in size between those. So Neptune is about 4 times the size of Earth. So for our solar system, as far as we know, there's nothing in between the size of Earth and Neptune. Let's come back to Planet 9 at the end of this explanation. So one of the surprising things from Kepler was when we went out in there and looked, it seemed like the most common kind of planet we were finding was in between the size of Earth and Neptune, between 1 and 4 times the size of Earth. And that was really interesting because it opened up all of these new questions, like how big can you get and still be rocky? And how big can you get before you start, accreting so much volatile and gas material at the start of your life that you become an ice giant? And is there something in between? Is there a type of composition of planet we don't have in our solar system? Like Bill mentioned, water worlds. Are there planets where it's just dominated by water, like an incredibly deep water ocean? And that would be super cool if there was a type of planet out there that we didn't have an example of in our solar system. So this was quite a surprise. Then when we looked even closer, what we saw is that these super Earths were actually broken into 2 populations. If you look at the sizes, there's actually a peak between like 1.5 to 1.8 times the size of Earth, and another peak between like 2 and 2.5. And in between, there's a valley. It's harder to make planets that are 1.8 times the size of the Earth than 1.5 or 2.0. And that was like, wait, what? So that opened up a whole new set of questions like, okay, what's going on with planet formation such that it's more difficult to make this kind of planet? So super Earths are this big mystery. And actually, that's one of the things that the TESS mission is trying to help us solve. So TESS is looking at all of the nearby planets, which are much easier for us to actually get measurements of their mass. Most of the planets that we find, we measure their size, but we don't know how heavy they are. So we don't know what they're made of. But because TESS is finding all the nearby planets, we can use other instruments to measure their mass. Once you have size and mass, then you have density, and you can start to say, oh, it's rocky, oh, it's gassy, that kind of thing. I mean, I'm always gassy, but we'll be able to find out if the planets are rocky. So yeah, this is super exciting that with TESS, we'll be able to unlock this mystery of what super Earths are. Coming back to Planet 9. Planet 9 is this theorized planet in the outer solar system, which they came up with as an idea to explain why some objects in the outer solar system seemed like they might be aligned in a certain way. That planet, if it exists, is theorized to be a super Earth, something between the size of Earth and Neptune. So it could be that our solar system actually has one of these most common kinds of planets. But, the jury's still out on Planet 9, but I think that would be very exciting if we actually did have one of these.
So maybe our solar system has a super Earth, but it's so far away that we have not yet seen it or discovered it.
Exactly. And we know it can't be too big because we would have seen it. So we've got limits, like it has to be big enough that it's pulling on these objects, but not so big that we wouldn't have seen it already, which is kind of why it gets trapped in this super Earth size. Good.
So another topic, which is, Andrew mentioned it twice in his presentation. The weirdness of a planet is also coming from the age of the star. Can you tell us a bit more about that? I know you one of the discoverer or the lead of this group that discovered this exoplanet in orbit around a white dwarf. Do you have a lot of those?
We're still in the very early stages of understanding planets around dead stars, white dwarfs. It's actually, I'll take that back. It's a historical curiosity that some of the very first planets that were found were around a dead star called a pulsar. And we found a couple of those early in the 1990s. And we thought maybe there are planets like these all over the place. But as we looked at more and more pulsars, we found out that they were fairly rare. Now we're in the very early stages of learning about planets around white dwarfs. And we're starting to ask those similar questions. How common is it for planets to survive the death of their star? And when they do, what happens to them? Do they just orbit around forever? We think that some stars, especially the really massive ones, die in what's called a supernova, a giant explosion. That can't be good for planets, you would think. So perhaps those planets don't survive very long, which is why we don't find planets around pulsars very often. But maybe the white dwarfs, which form in sort of a gentler, slow release rather than a violent explosion, can survive. So right now, we're really excited to be using data from TESS to try to search for planets around white dwarfs. TESS is really the first telescope that can do this en masse because it has so much higher data rates than previous telescopes. We can take a lot more data and we can download it to Earth because TESS is actually closer to Earth than previous telescopes like Kepler were. And that makes it really great for finding these planets. So hopefully in the next couple of years, I'll be able to give you a more complete answer to that question. But right now we're just starting to scratch the surface and see, can these planets even survive at all? And then do they move around after they are, after the stars become white dwarfs, or do they stay put, or do they get kicked out of their systems?
So a very basic question. When you found this exoplanet in orbit around a white dwarf, were you looking for this, or you found it because TESS had observed it?
We were looking for it. We had come across the very first object that I mentioned, WD 1145 plus 017 by accident in data from Kepler. So we thought maybe these white dwarfs are a good place to look for planets after all. So we were actually looking for it when we found this one, but we didn't expect it to survive. We were mostly looking for other planets that had been destroyed by their white dwarfs. So to see one that appears to have made it intact was a little bit of a surprise for us.
So we talk about the age of the star. Now let's talk about the orbit. Jessie mentioned and showed this beautiful system with which is in resonance, and you can make music with it. But in fact, maybe you should explain that the stability of orbit of exoplanet. I don't know to who I want to ask this question. Maybe Jessie wants to start.
Sure.
It's not that easy, in fact, to be a planet around a star. You are affected by it. The orbit changed. Maybe you can explain some what's the phenomena here.
Absolutely. So again, before we found exoplanets, the only system we had was our solar system. So all of our theories for how planets form and how they migrate and how they interact with each other were all geared towards reproducing our solar system, which has these rocky inner planets and these giant outer planets. So if your theory didn't do that, then you threw it away. It wasn't a good theory. Go back to the drawing board, try again. And of course, as soon as we started looking and actually finding exoplanets, the very first kind of planet we found were these hot Jupiters. So these are the giant gas giants that are only orbiting their star in just a few days. And there's this really interesting story where these planets had been predicted in a paper in 1952 by Otto Struve, who'd actually come up with a few ways that you might be able to detect them, ways which we now use to detect planets. But everybody kind of just was like, well, but you couldn't make a giant planet that close to the star. So why would you, that's a nice thought experiment, but we're just going to move on now. So between like 1952 and 1995, this paper has like 7 citations because everybody just thinks it's a crazy idea that'll never work. And of course, in 1995, we find the very first planet around a normal star, not a pulsar, is this hot Jupiter-sized thing. Now, how did it get there? That's the big question, right? That's why no one believed Otto when he was like, we could find these things. So we've come up with a few different theories for how planets could move. One of them is that when the stars and planets form, we believe it's from a giant cloud of material that collapses into a disk, like a big pancake. And then within that pancake, things start clumping together. And there's a lot of missing physics in here still, like why do things stick and not shatter? And all of this kind of very interesting stuff, which is very active field of research right now. But at some point, you make planets. while the disk of material is still there, it provides basically a torque on the bodies. So it could be that while the disk is there, planets migrate through the disk like molasses. It's sticky. It makes it hard for them to move. So they actually get moved by the disk being there. So that's one way we think planets move and might end up where we see them today. And particularly these compact systems in resonances that I mentioned. So TRAPPIST-1 is another very famous one that I'm sure some of our listeners have heard of, is another chain of compact resonances. We think those kinds of configurations must have happened slowly and smoothly, like with a disk of material. There's hardly any way that you can come up with which is very dynamic and violent, which ends up with this very compact, ordered set of resonances. It's just very difficult to do. But those violent interactions do produce things like hot Jupiters. If you have a couple of giant planets in your outer solar system and they get into a fight, like Andrew was describing with the rogue planet, one of them's going to win and one of them's going to lose. So we think that these giant planets, some of them get flung in towards the star and captured as hot Jupiters, and the other one gets flung out of the system and becomes a rogue planet for us to like find later as a little blip. So there are ways we think that planets interact very dynamically and scatter off each other, and they create these kind of much more spread out systems where there's all of this space because, you know, they had these violent interactions. So those are two of the ways we think that planets kind of end up in the orbits we see them today, either very smoothly and kind of gently while the disk is there, and you end up with these nice smooth interactions and these smooth resonances, or very violently and passionately, and everything gets spread and flung apart, and you end up with these weird configurations that we didn't expect.
So there is two takes from your answer that I would like to emphasize. One is that if you're a theorist and you have a crazy result from your modeling, publish it.
Absolutely.
Maybe in 40 years, we will find out that you were right. So don't be afraid. And
yes.
that's very
Since
important.
1995, that paper now has hundreds of citations because he was right.
So that's a main point. And then the second point is that you mentioned compact system and you mentioned distant system. Then there is this extra distant, which is the extreme case, those rogue planets. Andrew, you mentioned one of them. And this is a very fascinating idea that our galaxy may be full of those rogue planets. So can we estimate the number of them, or can you tell us a bit more about those, Andrew?
Yeah, so as I alluded to earlier, the best way we have to find rogue planets is through something called gravitational microlensing. And this takes advantage of the fact that, according to Einstein, everything that has mass, everything that has heft, bends light around it. And occasionally, if you have a star and it's very far away, and something comes in between you and the star at just the right angle, at just the right location, then it will take the light from the star, bend it towards you, and you will see that star get a little bit brighter. If you see that happen in the right ways, in particular ways that indicate that the mass of the object is very small, small enough to be a planet, you can infer that there might be a rogue planet out there because we don't see a star attached to it. We've been working on this, and I say we in the Royal Astronomer we, this is not my specialty here. Astronomers have been working on this for decades now, and recently we've started to have good success at finding these objects. Earlier in the 2010s, there was a suggestion that there might be many, many Jupiter-sized rogue planets in our galaxy, like 1 or 2 Jupiters for every star out there. It turns out that that doesn't seem to be quite right anymore. There are certainly some rogue Jupiters out there, but not nearly that many. Now we have this tantalizing evidence, and this recent planet that I showed, Ogle 1928 Bulge, something, I forget all of those digits. This one is tantalizing evidence that there may be lots and lots of smaller planets like Earth out there. So the jury is still out. We need to collect more data with our current surveys. We would love to get data from the upcoming NASA Roman Space Telescope, which will do a survey from space. When you go to space, everything gets better, everything gets easier. And hopefully we'll find out just how many of these lonely planets there are floating through the galaxy.
Thank you. Before we go to the next question, I just want to remind our viewer that now we are ready to take questions. So if you have some questions for our specialists of exoplanets here, use the Q&A, please, and write your questions, and some of them will be selected for the the end of this talk. So we talk about rock planets, and now the weirdest of the weirdest, the disintegrating exoplanets. Who want to take this? Who want to tell us a bit more about that? You mentioned one of them. Is there more? What can we learn from those? Why are they interesting?
Yeah, there's a handful of these disintegrating planets. They're fairly rare. Only some of them orbit these dead stars. Some of them orbit stars like our sun and are currently in the process of demolishing these planets, vaporizing them with their extreme radiation, and then eventually consuming them. And they are interesting because they, A, tell us about very, very small planets that we couldn't detect otherwise. And B, they can actually tell us what's inside of planets. So I'll talk about the small planets first. We think that in order for a star like our sun to completely vaporize a planet, make it so hot that it turns all of the rock into gas and have that gas leave the planet, it needs to be very small. And the reason is if there's too much gravity, if the gravity for that planet is strong enough, it may have its rock vaporized, but it won't fly off into space. So it needs to be relatively low mass, relatively small, and therefore have relatively weak gravity to disintegrate like that. We know of 3 of these objects, and we think that they must all be smaller than the size of Mercury. So that tells us that there are exoplanets out there smaller than the smallest planet in our own solar system. So that's really cool. The other thing that these disintegrating planets can tell us is what is inside of a planet. We think we know what's inside of the Earth's core, but we've never actually drilled down there. Our deepest holes into the Earth go barely scratch the surface. We have not even gotten into our Earth's mantle. So how can we possibly learn exactly what is in the center of a planet? If we were a geologist and we were trying to analyze a rock, what we do is we would take that rock, put it in our lab, crush it up, vaporize parts of it, and then look at that. So this is exactly what these disintegrating planets are doing. They're like natural laboratories for us to figure out what is inside of planets and what these planets are made of. We can't even do this for the planets in our own solar system. So this is maybe our best opportunity to learn what planets really are made of and what elements make them up.
Nice. You use those weird words at laboratories to really understand how planet forms and evolve. It's amazing what we learn in only 20 years, basically, on those world of exoplanets. Jessie, do you want to add something about this disintegrating exoplanets, or we go to the next question?
I guess the only thing I'd add is it's really interesting looking back at archival astronomy data, how early we actually had evidence of planets and didn't realize it. There are glass plates at Carnegie observatories from 100 years ago, which show spectra of white dwarfs. And we can see that those spectra are polluted with heavy elements that shouldn't be on the surface of white dwarfs. And now we know from work like what Andrew has done is that's because these planetary systems survive around white dwarfs and then get torn up. They disintegrate, they get eaten by the star, and the heavy elements from the planets and asteroids get left on the surface just for a long enough time for us to see. So this is just really fascinating that we actually have 100 years worth of evidence of planets around white dwarfs from these old glass plates.
That's a perfect transition to my next question. So we are doing a SETI talk, and at the SETI Institute, we are looking for life and trying to understand the prevalence of life in our galaxy. So those exoplanets that you mentioned are weird. Is that clear for everybody? But what do you think will be the consequences of having such a high diversity of exoplanets for life itself? What kind of life we will find? Did we already find life then? That's the question.
It's such a good question. So, it's hard to get ourselves out of the Earth-centric mindset, right? Like DNA needs these elements in this order and this temperature and this pressure, cook it all together and you make Earth-like life. And it's like, okay, how do we recreate those conditions in other places? And that's partly what's motivating our search for Earth-like planets. Like we know of one place where life happened and it was an Earth-like planet. But, closes off many other possibilities. Chemistry is crazy. It's so much more, unpredictable than physics. And there are other energy gradients. There are other chemical reactions that can produce, exothermic reactions and endothermic reactions that could become self-replicating. There are extremes here on Earth, even like we find life in places we don't expect, the very hottest places, the very coldest places. So it seems like life is very adaptable, right? Here on Earth, life seems very adaptable. So maybe we're being too narrow looking for Earth-like planets. Maybe all of these weird planets that we've talked about tonight, there's a way in some of them for life to happen, like Kepler 186f, which is the rocky planet around the M dwarf. Maybe it's not a big deal that radiation is that high. Maybe that's good. Maybe that increases the rate of mutation and life evolves much faster. Like, we just don't know. And it's so much fun to think about what kind of weird life could have evolved on these weird planets. And it comes back to a very important point you make. Maybe we've seen biosignatures already and we didn't know it. Like, we're looking at the atmospheres of these planets with telescopes like Hubble and James Webb when it launches at the end of this year. Maybe we'll see a molecule and then in 50 years we'll be like, that was it. It was in the data. We just didn't know yet.
Andrew, you want to add something to this?
I think that's exactly right. We get questions all the time asking, why do we focus on finding life around planets like the Earth? And really, we agree that's a problem. we should be looking for everything, but we don't really know how to do it otherwise. There are people who are trying very hard to solve this problem and trying to think of anything that could be a sign of life that doesn't look like what we have on our Earth. But I think probably we're going to have to find something that looks a little bit familiar for us to be confident. And then maybe with the benefit of hindsight, we'll be able to look back and say, oh, that actually looks like something that we would now consider to be evidence of life. We did that for the white dwarfs, where we see the first evidence of exoplanets 100 years before the first exoplanet was discovered, but we didn't know that that's what it was. We see that for planets themselves. The very first planet in Jessie's archive was published in 1988, but we didn't recognize that that was a planet because back then we didn't really know. So with the benefit of hindsight, maybe we'll find exactly the same thing with life and biosignatures or technosignatures.
So Andrew, I'm gonna put you on the spot here. We had a SETI live 2 months ago when you discussed, you were very relaxed at the end of the SETI live, and you mentioned something that was very interesting when you talk about the planet with the white dwarf. You remember about this? Mm-hmm. Can you maybe say a bit about that?
Yeah. So one of the things that really excites me about trying to find planets around these white dwarfs, these dead stars, is to figure out if life in a solar system can persist even after a star dies and runs out of hydrogen fuel. And we think that that might be possible. White dwarfs are the cooling remnants of these stars. They're no longer producing their own energy, but they have a lot of leftover energy themselves. So they glow, and they will glow for very long periods of time, much longer in some cases than the star itself will survive. So this glow could, in principle, provide the energy that life needs to get going. It could provide the energy to keep a planet warm and to power the chemistry that governs, the biological reactions. So the only question is, can a planet get close enough to the white dwarf to huddle near that very cool burning out ember and stay warm enough for this to happen? And if we start finding planets like WD 1856, that gives us a lot more hope that planets actually can come close to the white dwarfs, get close enough to be warm in the habitable zone where it's warm enough for liquid water to exist and survive, so that potentially you can have life form there. And the white dwarfs can last very long time. WD 1856 plus 534 has been a white dwarf longer than our sun has existed. So there's plenty of time for life to grow and survive on these planets if they have a place to start out. So I'm really excited about trying to understand that direction in the future.
Interesting and remarkable what we can start thinking about now we know more of those exoplanets and the diversity in the context of the search for life. And I think your generation of astronomers will be the one that will basically get the breakthrough of finding this life and going through the data and tell these ancient astronomers like me, hey, you were blind. There was life here. You just did not see it. So kudos. We talked about 9 exoplanets at the beginning, and I'm going to ask the team to put the poll on. And we're gonna ask you to choose the exoplanet, the weird exoplanet that you prefer in all of them. Of course, you have to make one choice only. It doesn't mean that we are not gonna like the other one. It's just that I'm kind of interesting to see what you as the public and the audience thought about the most interesting, the weirdest of those exoplanets. And we're gonna take questions. Thank you very much. Rebecca, you ready?
I think I am ready. There's a ton of questions, so we're trying to stay on top of them, and we're not going to be able to get to a lot of them, but thank you everybody for all your questions. So I think this first question, maybe we'll start with Jessie on this. And you touched on the topic of next generation space telescopes, but sort of two-part question. What are the next generation space telescopes that you're most excited about that will give us a new kind of understanding of exoplanets? And also, are there any ground-based telescopes that will help us find Earth-like or Sol-like solar systems and planets in those systems?
Oh yeah, those are both very good parts of questions. So the very upcoming generation of space telescopes is James Webb, which is going to launch at the end of this year, and the Nancy Grace Roman Space Telescope, which is going to launch in 5 or so years. Those will really revolutionize our understanding of exoplanets. Webb is designed to peer into the atmospheres of these planets and really help us start to understand what molecules and atoms, at what layers, are there clouds, are there hazes, all of this really exciting stuff about the atmospheres of planets. So Webb is designed to study individual systems quite deeply and to help us understand individual planets. Roman, so this, Andrew mentioned this, the Nancy Grace Roman Space Telescope will do a survey of microlensing planets. So where we talked about the fact that we're sensitive to hot planets so far, and the detection techniques are kind of marching outwards. Microlensing is actually a very complementary technique, and it's sensitive to cold planets. So if you add all of the data from Kepler and all of the data from Roman, we'll actually have the census of like the entire contents of planetary systems, 10, 15 years from now, which is really exciting because we'll actually start to be able to add up all of the habitable real estate in the galaxy and to start really thinking about that. In terms of ground-based telescopes, one of the sorts of technological breakthroughs we're trying to make is to directly image these planets. So this is where you have very exquisite instrumentation where you try and block out the light from the star and look for the tiny specks of light. Planets are so faint and stars are so bright. This is very difficult. But if you have a big enough telescope on the ground, which is what we're envisioning building, these 30-meter telescopes, you can, if you have the right instrumentation, you can actually block out the light and actually see the planet. So we're hoping that with these big ground-based instruments that are being built, there's like a suite of 3 really large ground-based optical telescopes. So there's the European Extremely Large Telescope. We should not be allowed to name things. There's the 30-meter telescope. We should not be able to name things. And there's the Giant Magellan Telescope, which is actually not too bad. That's actually kind of a bit of a grand sounding name. So those are 3 big ground-based telescopes that are going to get built, which are going to help us actually take images of planets, which is very hard to do right now and only works for the biggest, hottest planets.
Okay, so Andrew, Jessie mentioned a couple of the different observational techniques that we use to find these exoplanets. We've talked a little bit about transits and we've talked a little bit about gravitational lensing, but can you explain some of these methods a little bit more in detail? A lot of the audience is curious as to how we're finding these.
Yeah, so we use a suite of different techniques, most of which seem needlessly complicated, but it turns out these are the ones that are easiest for us to do. So Jessie mentioned the obvious one, direct imaging, which is where you take your telescope, you look at the star, and then you look for little specks of light near it that are planets. It turns out this is really hard to do. If you wanted to find an Earth-like planet around a star like our sun, that's about as hard as looking at a lighthouse with a firefly flying next to it about 3 feet away from a distance of New York to Los Angeles, so about 3,000 miles. It's really, really hard. So instead, we take shortcuts. And one of the things we do is we look for what are called transits. If you happen to have a planet whose orbit is lined up just perfectly so that here's a star, here's the planet, it passes in between the star and our telescope, we can see that part of the light of the star is blocked. The planet casts its shadow on us. If we see that shadow come around over and over again, we can infer there's a planet there. That is the most prolific way we've been able to find planets. That's what the Kepler telescope used. That's what the TESS telescope uses right now. Another way is called radial velocities. This is taking advantage of the fact that if you have two things orbiting each other, not only does the planet go around the star, but the star moves a little bit as a result of the planet. We can measure that motion with our instruments. We can try to see how fast a star is moving towards us or away from us, using the same principles that make it sound like when an ambulance is coming towards you, the pitch of the sound is higher, and when it's going away from you, the pitch of the sound is lower, called the Doppler effect. We can also look for that wobble caused by the planet tugging the star in the other directions and see the star moving very slightly in the sky. That's something that the European mission called Gaia is doing right now. And hopefully they're going to give us a big list of stars with planets that orbit them in a couple of years. We're very much looking forward to that data download. We talked about microlensing, which is where you look for the gravitational pull of the star, or the pull of a planet, I'm sorry, slightly changing the direction of light, bending it towards us, so we see little blips of light when we wouldn't have seen them otherwise. What am I forgetting, Jessie? We can look for when one planet tugs on another. Yeah. So if you see planets that are orbiting around and they might transit the star, go in front of the star and block its light, if the shadow of that planet sometimes arrives earlier and sometimes arrives later, you can guess that there must be another planet nearby causing it to do that by tugging it back and forth with its own gravity. Anything else? I think that's the big ones.
The rest are very minor. There's things like orbital brightness modulations where you don't actually see the transit, but you can see something getting brighter and dimmer, and you know that there's a planet that's kind of like the phases of Venus kind of coming in and out of view. There's the pulsar timing, which is another flavor of transit timing. A very brand new one that we just added last year to the archive is disk kinematics. So ALMA, which is this big telescope in South America that uses millimeter wave light, can image protoplanetary disks, so disks that are forming planets. And what we can see when we look at these disks in high resolution are little walls and vertices and clumps. And you can infer from the kinematics that there's something in there of a certain mass that must be perturbing all of this material. So this is like literally watching planets get born. So that's the most recent detection technique that has been successful that we've added, which is disk kinematics.
Awesome. Jessie, this is another question for you. You mentioned citizen science a little earlier before. So people are asking, how can citizen scientists get involved with looking for exoplanets? And can amateur astronomers, even with small 8 or 12-inch telescopes, find exoplanets? Find exoplanets. Or does sort of atmospheric interference get in the way and make that more difficult?
Yeah, absolutely. Both of those are very exciting questions. Okay, so citizen science, we have several projects that you can get involved in. The most prolific one right now that I would suggest is the link that I put on planethunters.org. So we get all this data from TESS, and Andrew mentioned like the data download rate is so fast. We're getting, thousands and thousands of light curves every few weeks. And so we have software algorithms that we write. Andrew worked on several to look for planets in them. But actually, the human brain is really, really excellent at pattern recognition. When we were hunters in the grass, we needed to be able to tell what was zebras and what was tigers. So we're really good at pattern recognition. And if we look at data, it's actually really easy for us to say that's a transit, that's not a transit, where it's hard to explain to a computer what the difference is. So one of the fantastic ways that citizen scientists have been able to help us is just look at the data and tell us where they see transits. And this helps us find all of the transits that the software misses because the star is doing something, or there's only one transit around this star. So it was hard for the software algorithm to find and you know, if we just have, it's crowd power, right? It's crowdsourcing it. If we have tens of thousands of people looking at the light curves, we can keep up and they can contribute. So actually 20% of the candidates that TESS announced last year were found and contributed by the community, which is super exciting. So that's absolutely how you guys could get involved, is to go and just look at the data. And it's really interesting because stars are not just like sitting there waiting for planets to go in front of them. So the data is all very weird and woolly anyway. You're going to see variable stars, you're going to see eclipsing binaries. It's very cool to just look at the data. And then amateur astronomers with small telescopes, oh my God, they are so essential to the success of the TESS mission. And I'll tell you why. TESS, in order to do this incredible big all sky survey and have this incredible data rate, has giant pixels. So this is a CCD camera with pixels that take up 20 arc seconds. So for the amateur astronomers among you, when you're out at a good site and you know you've got 1 arc second seeing or 2 arc second seeing, the TESS pixels are 20 arc seconds. These are big fat pixels on the sky. What that means is a given pixel can and usually does have multiple stars in it. So TESS can tell us something in that pixel is doing something, but we need to go and use other telescopes to look at with higher resolution so we can actually separate all the stars and watch them when we expect to see something happening and say, ah, that one, that's the star that has the event on it. And that's really important. So we have a whole follow-up community around the globe of amateur astronomers using much smaller telescopes than 12 inches. 12 inches is a bonza big telescope for an amateur. And you can absolutely do this kind of photometry. There's a lot of software that's been pre-written for people. If you have a telescope and a CCD, you can absolutely contribute and help us find planets.
And it doesn't have to be in a really dark site. I think one of the best observers we have on the TESS team lives in Perth, Australia, and does it from his backyard in the suburbs. So even if you live in a place with light pollution, you can contribute.
That's really neat. I'm very excited for that. Andrew, I know, correct me if I'm wrong, but all the planets we've been discussing tonight are in the Milky Way. Is there a way to see planets in other galaxies yet?
It's very hard. There are some ways that we think we might be able to. One of them is by using microlensing, which is where we look for light from another star that gets brightened because a planet passes in front of it. That would potentially be a way to do it, because the main challenge with looking for planets in other galaxies is that the stars are just so far away, they're very dim, so we can't get very good data on them. And planets make very small impacts on their star's light. So if you want to have a capability to measure that, you need lots and lots of light, lots and lots of photons pouring into your telescope. And it's just hard to do that from something more than a galaxy away. We do think that there will be opportunities, though, in the future. One thing that we're looking forward to is the commissioning of the Vera Rubin telescope in Chile. That's going to be a giant telescope, 10 meters across, so 30 feet for the Americans. And it will take images over and over and over of different parts of the sky, including other galaxies. And based on some calculations that have been done by, I think actually someone at the NASA Exoplanet Science Institute, Mike Lund, we should be able to find planets in other galaxies using this facility. By looking for their transits, by looking for when the planets cast their shadows on our telescopes. Yeah, the transit method seems to be one of the easiest ways to do that so far, but we haven't done it yet, I think. Yeah,
there was one tentative claim of a microlensing event in the Large Magellanic Cloud, which is like a nearby dwarf galaxy, but I think it didn't really pan out. One thing I'll add to Andrew's answer, something that's very cool is our galaxy actually eats other galaxies. So our galaxy at this point is now composed of many smaller dwarf galaxies that it kind of ate over the last 13 billion years. And one of the things we found is exoplanets that belong to streams of stars that were clearly once a coherent dwarf galaxy that our galaxy just ate and shredded. So we have found extragalactic planets in the sense they formed around a star that formed outside our galaxy, but is now inside our galaxy. It's a little bit of a cheat, but we do have extragalactic planets.
Okay, I know we have a lot of questions, so I'm going to ask you to ask 2 more questions, but let's make it a short answer, please.
Okay, I think I have a short a short question with hopefully a short answer, which is people really loved the sound of the planetary system that you played. They thought it was beautiful. And so one of the questions is, where can they find more recordings of what planetary systems sound like?
Fantastic question. So the website is called systemsounds.com. And this is a group in Toronto who do sonification of astronomy things, including Chandra images and Hubble images. And then they have a suite of these exoplanet resonance music, basically. They also made a really lovely, for when we hit 4,000 exoplanets last year, they made this incredible visualization of the sky with all the exoplanets appearing as we found them. So that's my short answer. Systemsounds.com. Go check it out.
Okay, I don't know if my question is necessarily short, but I'm going to direct it first to Andrew, and then Jessie, if you want to take a shot at it. What are your thoughts on exoplanets around Alpha Centauri? I know there was a paper that came out last week that talked about a new technique for finding one that possibly found one. Have you read anything about that? Where do you think we're going on that particular observation?
Yeah, I read that paper. So this is not the first planet that has been theorized around Alpha Centauri. There was famously a planet that was claimed in 2012 that later turned out not to be there, around Alpha Centauri b. Then recently, there was this announcement of a possible planet around Alpha Centauri last week. That was done using direct imaging. So what they did is they took their telescope and they sharpened the images as much as they could to get rid of turbulence from our atmosphere. And they looked in wavelengths of light that correspond to very cool objects. So this is what we call the thermal infrared. And they looked for a little bright dot near that star. And they may have seen one. Now, it's very tentative. It's right next to the star. It's close enough that it's possible that that's just a little bit of starlight that leaked out. We have what they have is they have this fancy device called a coronagraph, and what it does is it's basically like taking your thumb and putting it over the sun at nighttime or in the daytime to block the sun so you can see stuff nearby, or taking your hand like that. But it's a more sophisticated version that goes inside your telescope. So it's right next to the edge of that coronagraph, and that's kind of a scary place to find something, because that means that it could just be light that leaked out from behind your coronagraph. It will be very interesting to see if they're able to improve upon their coronagraph, take more data, and see if that little piece of light is still there. If it is, then we might have to start thinking seriously about whether there is a planet near orbiting Alpha Centauri that we were able to actually take an image of. It would be super, super exciting, because then we could actually start looking at its atmosphere and looking to see if there's anything living there, or at least anything that we can recognize.
Okay, Jessie, you want to add something about this exoplanet before we go to the next question?
I mean, just to emphasize for everyone, Alpha Centauri is the closest star system to us. It's got 3 stars in it, Proxima Centauri and Alpha Centauri A and B. And so far, one of them has a rocky planet in the habitable zone. Another one seems to have a planet around it. And the third one had the planet that Andrew mentioned that got taken away. So this just really points to the fact that our very closest stellar neighbors in our galaxy have planets around them, and they have rocky planets around them. And that's so exciting. Like, this is our next door neighbor. This is, borrow a cup of sugar. Next door neighbor has planets around it.
Thank you. So I'm going to share the result of the poll. I don't know if you can see it. So people seem to like the K2138 system. I don't know if it's because it was discovered by citizen astronomers, or it's because you made music with that, but it seems to be the one that got the attention, followed by HD 189733b, which is the hot Jupiter with liquid gas raining, etc. Of course, yeah, Kepler also got a lot of attention. Kepler 186f, 16%, and Ogle 216 BLG 19.
We don't have enough time left. Don't say the whole name. It's too long.
The terrestrial planet without a star, the rogue planet. Okay, so my last questions before Bill give us some the last word. So what's next for you, Jessie and Andrew? What's your next big project? Where do you see yourself in 10 years in the study of exoplanet? short, please?
Sure.
Jessie.
Okay. 10 years. So what I'm really hoping that's happening in 10 years is that James Webb has unlocked a whole bunch of new mysteries about exoplanet atmospheres. There's a European mission called Ariel, which is going to do even more work on exoplanet atmospheres. And what I'm particularly excited about with Ariel, it's going to do enough planets that we'll be able to do statistical studies of how common are cloudy planets, how common are clear atmosphere planets, how common are water-rich planets, because again, that just feeds into this information that we need to work out how common the conditions that we need for life are. So 10 years from now, I'm hoping that we're really getting close to this answer of, are planets like the Earth with like water, oxygen, atmospheres, is that common? Is that rare? Like, let's find out.
And you, Andrew?
I'm looking forward over the next 10 years to no longer thinking about planets, but thinking about systems. So as Jessie mentioned, we can only right now look at very small slices of the planets in our galaxy. We can look at the ones that happen to be lined up so that they transit. We can look at the ones that are close in so we can see the pull that they make on their stars. When we get more data over the next couple of years, what's going to happen is we're going to be able to start looking at the same stars with different techniques, and we can start piecing together that this system, which has a small planet orbiting close in discovered by TESS, also has a further out planet that was discovered by ESA's Gaia mission. And maybe it has another one even further away that was discovered by these direct imaging missions. And as we start combining all of our techniques, we start marshaling all of our telescopes to look at the same stars, our closest neighbors. We can start asking questions like, is our solar system unusual? Or is it just that we haven't been able to see it yet because we lacked the technology?
Thank you. So I just want to mention to our viewers, we didn't answer to all your questions, but this video will be on YouTube later on. So if you want to ask questions, you can add them on this YouTube video, and we will take the time if we have to answer to some of those questions. Okay. Thank you very much, Andrew and Jessie, for this amazing this conversation. And Bill, last word, please. Thanks.
Great. All right. Thank you, Frank. And of course, thank you, Andrew and Jessie. What a fantastic topic. And it was just a great presentation and discussion. I have to admit, I'm particularly impressed with that planetary system with its planets in resonance. I mean, when the cosmos gives out music, that's pretty magical. I do have a special place in my heart for the planets being torn apart, but it does seem like the Death Star is real. It's just not a spacecraft with a laser beam. So our guests today will be receiving a mission patch from the SETI Talks series and the highly coveted SETI Talks mug. In fact, there's only one of these mugs for every speaker who's ever been a lecturer or panelist on SETI Talks. So if you have one, you're part of a very special and unique community. In fact, they're so rare, I don't even have one here to show you. But that's going to be fun, and you can expect that in the mail in the coming days. Where did some of our guests join us from? Well, they were from all over the place. In the US, we had people from New Jersey and Dallas, and thanks folks from Dallas, Texas for joining us. I know you guys are going through a hell of a storm system and cold period right now. So we're hoping you get your power back and are staying warm and safe, but great that you could join us. Illinois, New York, California, Florida, Maine, Nevada, Delaware, Maryland, Virginia, DC, Pennsylvania, Utah, Oregon, Indiana, Massachusetts, Arizona, Tennessee, Minnesota, and Homedale, New Jersey, which was given to us by Coordinates. We had folks overseas visiting us from Japan and Australia, Macedonia, Canada, China, Gibraltar, Singapore, Argentina, and Guatemala. So awesome, and thanks so much for all of you for joining. I do want to remind you all that the SETI Institute is a nonprofit research, education, and outreach organization. We're supported in part by donations from the public. That means people as well like you. We bring these lectures and other events to you at no cost, but we're always very grateful for any and all donations that allow us to continue bringing these stories of extraordinary science to all of you. So we invite you to join our quest and become part of our community. You can go to our website at SETI.org, SETI.org, for more information. You can make a donation if you're so inclined, but certainly sign up for our monthly science newsletter we call Journey. And I'd like to give a special thanks and shout out to Rob, who joined us tonight on YouTube. or I think it was Facebook actually, and already made a donation. So thank you, Rob. And a big thanks to all of you for being with us today. Of course, thanks again to our guest speakers, Andrew and Jessie, and to Frank, Rebecca, Beth, Lee, and the rest of the team at the SETI Institute who make this wonderful series possible. Don't forget to visit our YouTube channel and tour the amazing array of lectures, presentations, and other videos. And most importantly, don't just come along for the ride. Join us at SETI.org. Be part of our mission and join our team. The search for life beyond Earth is a journey of ultimate discovery. So thanks for being with us, and good night.
Bye-bye.